In this video, I would like to derive the formula for electric potential energy. And the setup for this is I'm going to have a positive charge over here. That's going to be the source charge. And then over here, I'm going to have a test charge. All right. And I'm going to assume that they're both positive. If one of them was negative, then that would change the result by just changing the sign. Okay, so I'm going to set up an axis here where the axis goes like this, and I'll call it the r axis. So the distance is 0 when the test particle is right at the source, and as the particle's further away, r gets bigger. Okay, and let's say that the particle started out a little bit closer and it has moved to this new location. Okay, so its original position is r initial, and then its final position is r final. All right, and furthermore, let's say that there's some external agent that is moving the particle. So it's not just moving under the force of the source charge, it's moving under the agency of some external object. Okay, so I'm going to draw that as a hand. Okay, so here's my hand. Okay, and the hand has moved the particle from its initial position to its final position. Okay, so in particular, I want to assume that the speed is constant so that it is not accelerating. So if the acceleration is equal to 0, then I can draw a free body diagram for the particle where there is a repulsive electric force. So this is a force, the electric force from the source charge, and then balancing that out because the acceleration is 0, I'm going to have a force from the hand. Okay, so that's my external force. And those two forces are equal and opposite because the acceleration is 0. Okay, so what I'm going to do then is I want to calculate the external work. All right, and remember that the work is just defined to be the integral of the force dotted into the displacement. And in this case, the displacement is going to be in the r direction. So it's moving, along that r axis. Okay, and in particular, the external work is done by the hand. So this is going to be the force from the hand, Fh, times ds. All right, so the magnitude of the force from the hand is the same size as the magnitude of the force from the charge, which is going to be k times the source charge times the test charge over r squared. And the direction is going to be towards the source charge. So the hand is like exerting a force to the left in this case, which means that that's in the negative r hat direction. Okay, so there's my force. And I'm going to dot that into dr because the displacement, ds, is along the r hat direction. Okay, so what I have here is a dot product between two vectors. R is to the right in both cases, so r hat is to the right, dr is to the right, but I have a minus sign in there because the force was actually to the left. Okay, so because of that, I can actually calculate this dot product. It's just going to be the magnitude of those two things, r hat and dr vector, which is just dr. Okay, so what I'm going to do, different color. Okay, so this is going to be the integral of minus k q source q test over r squared dr. Okay, so essentially all I've done is try to be really careful about the sign here. If you weren't careful and messed it up, you would just get a sign error, which would be pretty obvious. Okay, and in addition, this is actually a definite integral, and so I'm integrating from the initial position to the final. So from our initial to our final. Okay, and that is the amount of external work that is done. Well, this one we can calculate really easily. It's just 1 over r squared, and everything else is a constant. So when I integrate that, what I'm going to get is all the constants, so k, qs, qt over r. So the 1 over r squared is going to become negative 1 over r, which will cancel out the negative sign. Okay, so this is what I get. And I'm evaluating this from the initial position to the final position. So then if I write that out, I'm going to get k qs qt over our final minus k qs qt over our initial. All right. So in this case, because the speed is constant, the kinetic energy is constant, and so the only energy that's changing is the potential energy. And so what we have is that the external work is equal to the change in electric potential energy, which is, of course, U final minus U initial. And since we calculated the work, and we're associating that with U final minus U initial, this one's U final, and this one is U initial. Okay, so this gives us a formula for the potential energy. The potential energy is just k q1 q2 over r, and that's it. As usual with potential energy, because we only calculated the difference in potential energy, we could add some arbitrary constant if we wanted. So we could take that and do plus u0. But whenever you calculate a change in potential energy, that would cancel out. And so it just complicates things. And so we almost always choose that potential energy to be 0.